I did not get. All right. So chapter 2, we're going to be looking at chemical formulas and composition of stoichiometry. Okay, stoichiometry may sound like a really long word or may not make sense to you right now, but really it's just a kind of a spin-off of dimensional analysis. So where you guys were converting from inches to feet or meters to kilometers or whatever, it's very similar. It's just now we're going to be pertaining this to chemical reactions and compounds. Chapter 2, we're really looking at one compound and being able to convert from grams to moles. If you don't know what a mole is, we'll talk about that today, and to molecules. Chapter 3 gets a little bit more complicated because we're looking at a chemical reaction and being able to convert from one compound, a quantity, to another totally different compound in the chemical equation. Okay, but today is very, very important. Some of you that have had, a good background in chemistry, you've probably already converted from grams to moles and all that. But for those of you that haven't, that's fine too, because we're going to be going through that today, and hopefully you'll get lots of practice on this. Okay, today we're just going to get to, 1 through 5 probably. So we're going to look at chemical formulas. This first part is probably most of you probably understand this so far, just being able to look at a compound and know what that means. We're going to look at what a mole represents. In chemistry, we're going to look at formula weights and molecular weights, also, and molar mass. And then the last thing I think we'll actually get to will be number 4. We're going to look at the percent composition of a formula. Okay. A chemical formula shows the chemical composition of that specific substance. So it gives us the ratio of the elements or the atoms that are present in the molecule or the compound. Okay, if you have what we call a monatomic element, this just means that you just have this one single element or atom from the periodic table. Okay, we have diatomic elements. That just means we have 2 atoms of the same element. Okay, so oxygen and hydrogen and your halogens exist as diatomic molecules. Okay, so you will, if I say methane reacts with oxygen, okay, oxygen always exists as O2. Okay, can anybody explain why do you think it would exist as O2 instead of just oxygen, just one single atom? Anybody? Yeah, it's more stable. It's electrons. So if you look at the formula, so oxygen wants to exist as 2 oxygens bonded together because it completes its octet. So we talked about electrons, and that's why. So it's not just a coincidence. The same for hydrogen. It wants that one single bond. So you have a hydrogen, and that single bond in between so that they fill their octet of 2, actually, not really an octet there, but it's 2 electrons in the outer shell. Okay, we have some more complex, so we have like ozone, P4. These aren't as common as your diatomic molecules, so these are just more complex. They have more of the same atom bonded together. Okay, but the main one we'll be looking at majority of the time are just our compounds. Okay, so back in chapter 1, we defined a compound, but so like you have water, or you have any of your glucose or sucrose or any of those, and so we look at majority of our compounds or majority of molecules are in the form of compounds. Okay, so if we look at a compound, what do those numbers mean? Okay, so if we have HCl, hydrochloric acid, our ratio, so that subscript is understood as 1 here. Okay, so the subscript is what tells you how many atoms you have present of each atom in the molecule. Okay, so for HCl, we have 1 hydrogen and 1 chlorine atom. Okay, so this is pretty basic, elementary here. But for water, we have H2O. We've looked at the structure of this. We've seen why it exists as H2O, and we've seen how it completes its octet through the Lewis structure. So we have 2 atoms of hydrogen and 1 oxygen atom. Okay, and so the same for ammonia. We've got 1 nitrogen and 3 hydrogen atoms. And then this is propane. C3H8, we have 3 carbon atoms and 8 hydrogen atoms. So hopefully you've already picked up on this through the semester. Okay, but those subscripts indicate the number of atoms of each element in a compound. Okay, so this is just referring you to, it's actually page 45. Y'all have a new book. It was on page 50. All they did was shift the pages around, but they make us go to the new edition. So, but page 45, or you can look at the handout that I have on Blackboard. So this is kind of just referring you to that handout. And there are compounds that the highlighted ones are actually the underlined ones. Those are the ones that you need to know. Okay. I'm actually going to go through this, actually skip through this. This is great if you want to go back and look, but we've already learned this chapter goes into your polyatomic ions, but I chose for us to learn that when we were naming last week. Okay, so this is the same thing. If you want to go through and be sure that you know how to name these, it's good practice, but we've already discussed this. Yeah, so these would be good to go through. Be sure you know how to name and write formulas for both of these. Okay, so we discussed, and actually on your last test, there was a question about atomic weight or a mass number. Okay, so we know that those two things are different. Okay, the atomic weight is the number that we find on the periodic table. Okay, so it's not a whole number. It has these, how many ever significant digits the periodic table has there varies sometimes. Okay, and this number is the weighted average of all of the isotopes of that element. So it takes the average. Okay, and so that's the number that is put onto the periodic table. Okay, so it's that lower number, and our units that we've seen so far for this number have been AMU, and that just means atomic mass unit. Okay, but what we're going to look at and get to here in the next few slides is what does this number really mean? Why, is it in grams? Is it in what is it, related to? How did they come up with this number, and what does this value represent? Okay, so in answering that question, I'll go ahead and I guess tell you, and then we'll look at why. Okay, but that number represents the mass or the atomic weight for 1 mole of that element. Okay, but before we go further, we have to know what a mole means. Okay, so in chemistry, when you're in the lab, even dealing with small scale reactions, you're still dealing with thousands of atoms. Okay, so what we do in chemistry, we represent these enormous numbers, and we want to describe matter or atoms or our molecules in a way that is large enough for us to see and handle. So how can we measure this out in the chemistry lab? Okay, and so that's where the mole comes in. Okay, just like you say I have 12 eggs. Everyone knows that that would be the same thing as saying I have a dozen eggs, or I have a dozen pencils. Everyone understands that to be 12. Okay, well that's the same for a mole. If you hear 1 mole, that is the same thing as saying 6.022 times 10 to the 23rd things. And we'll talk about what these things are here in a second. Okay, so 1 mole, this is called Avogadro's number. Okay, so it's also represented, I'll shorthand it as Na. Okay, and this is a number you want to commit to memory. Okay, you'll see it written as 6.02 or 6.022. I'm not that picky, so whichever one you want to learn. Okay, times 10 to the 23rd. Okay, so that's the same thing. Just like if we have a dozen eggs, if we have 1 mole, it means that we have this much or this amount of things. Okay, so in chemistry, our things that this represents are going to be particles, atoms, molecules, and also at times ions. You may want to add that in there. Okay, so when I'm asking you, or when we're looking at problems, one of the hardest things for students, I feel like, is to go through and decipher a word problem. Okay, we're about to start entering calculations. Some of you love math, others of you don't. Okay, so this is kind of the beginning of it. But when you're looking at a problem and it asks you or gives you molecules, atoms, or particles, you want to automatically start thinking Avogadro's number. I've got to use that somewhere. Okay? So the mass of 1 mole, this is what our periodic table is representing. All of the elements on the periodic table are per 1 mole. Okay, so whatever numbers are on there, that atomic weight, okay, is out of 1 mole. Okay, so this will be really important when we start doing some calculations. Okay, but the mass of 1 mole of an atom, okay, for a pure element in grams is numerically equal to that atomic weight on the periodic table. Okay, so if we look here, we've got these common relationships. Okay, just like when you looked at your conversion factor list and you needed to go find how many milliliters are in a liter or whatnot, that was your common relationship that you were trying to find to plug into your equation or to do the dimensional analysis. Okay, this is the same thing here. Okay, so if you look at titanium, okay, if we have 1 mole of titanium, okay, this means, so if you look at your periodic table and you look at the atomic weight, that you have 47.88 AMU, atomic mass unit. Okay, that doesn't really help us much when it comes to calculations. We don't typically use AMU as our unit. Okay, but we can also say that we have 47.88 grams of titanium. Okay, so this is huge, that common relationship there, that we can use grams. We can also go from moles, so here we are in grams, okay, and if we have 1 mole, we always have 6.022 times 10 to the 23rd atoms. Okay, so this is very important that you understand this. Okay, so if we look at magnesium, all right, so we look down at its atomic weight here. Okay, so this number here is equal to 1 mole, which is also equal to 6.022 times 10 to the 23rd atoms of this. Okay, so I have this capitalized and highlighted or bolded here, okay, because every time when you're doing a calculation, and you'll see where this is important because we're going to do lots of these, okay, in any shape, form, or fashion, if you go to the periodic table to find this number, to use it, it's always going to be out of 1 mole. Okay, so you may have 24.305 and in the denominator per 1 mole or vice versa. Okay, so your unit factor for this number is 1 mole. Okay, so we use the mole to measure and help us describe quantitative relationships among elements and compounds. Okay, so if you think about when you go to the lab and I was to tell you measure out 3 moles of magnesium, okay, what do you think you're going to do? What does that mean to you? Okay, you're going to have to convert from moles to grams. Okay, so when you go over and you measure your object or whatever, your chemical on the balance, it's going to give you grams, right? Okay, so we have to be able to convert moles and grams. Okay, so that's kind of our idea. However, the mole is what we use to express this large quantity of atoms. So if I was to tell you, even a small sample, if we didn't have mole as our common representation, we'd be telling you to measure out trillions of atoms. Okay, and that's just not possible. Okay, we've got to look at it in a larger unit, and that's where we get the mole. Okay, so that's what we're going to use, and we're going to be able to convert from grams to moles today, and then later we'll be adding to that. All right, so the first thing we want to do, these first 2 problems are just totally essential to, you have to know how to do these problems to make it through the next few chapters, or really through the rest of the semester. Okay, so these are imperative that you understand these. Okay, first we want to look at our problem. We're asked for grams. We want to know how many grams of magnesium are in 3.451 moles of magnesium. Okay, for these problems, if you're given, whatever quantity you're given, so we have 4 significant digits that were given in this problem. Okay, so in your answer, you want to report to me 4 significant digits. Okay? All right, so you might remember when we were looking at converting from certain dimensions to other dimensions, what I always said to do first, to at least just get a half a point or a point. Okay, write down exactly what's given to you. Okay, so that's what we're going to do. We're given 3.451. Okay, but now it is very important. Okay, I know right now this is not very complicated. Okay, but you've always got to write your units. Okay, this will help you. Later on, you'll start getting confused if you don't write out your units. Okay, so we've got moles. Okay, but we don't just have moles. We have moles of magnesium. Okay, so you want to write out that here it's just a single element. Okay, later we're going to be looking at compounds. We're also going to be converting from one compound to a totally different one. Okay, so that's where it comes important that you write down the unit and the compound, or here we just have an element. Okay, I go ahead and do this, like this, and if my units are moles of magnesium here, then here, to cancel, I have to have moles of magnesium. Moles of magnesium. Okay, so we're trying to go from moles to grams. Okay, so if we think back, we even had a slide with magnesium on there, so we had that element there. Okay, what's going to be our common relationship? If we were to have a conversion factor sheet, kind of think of it that way. You're going in there and you're trying to find what's common. How can I get from inches to feet? Or, hey, here, how can I get from moles to grams? What do you think? What are we going to have to use? Do what? Okay. Okay, it's not the mass number. What's it called? Remember, the mass number is a whole number. We have to be given that. The atomic weight, right? Okay, so if you look back at that slide, that number there on magnesium is, I think, 24.305, we'll call it. Okay. And we'll discuss why I put it up here in a second. 1.3. Okay, so we go to the periodic table, and that's where we get this number here. Okay, so our units for this, if we look back, that 1 mole was equal to grams, also equal to atoms. So here we're looking for grams. Okay, so we would say that we have grams of magnesium. Okay, so what's going to go on the bottom here? Always 1, exactly. So if you go to the periodic table and you find this number, the atomic weight, it's always based on 1 mole. Okay, that's how we can convert, and we're going to see obviously a lot more complicated conversions, but the one common thing is when you go to the periodic table and you add up or you look at the atomic weight, it's based on 1 mole every single time. That's what the periodic table is built on. Okay, so we're going to just have 1 mole of magnesium. Okay, so we multiply 3.451 times 24.305. Okay, and whatever number that you plug in here for your test or whatever, this will be exactly what's on the periodic table that I give you. Okay, so sometimes they'll just stop at 24.3 or whatnot. Okay, so it ends up giving us 83.89, it looks like. Okay, so these units cancel, and we're left with grams of magnesium in the numerator, and that is our answer. Nope. Anytime you look at the atomic weight, you always divide by 1. Here in a few minutes, we'll see when we use Avogadro's number, though. Okay, now we're just going to look at this problem in reverse. So we went from moles to grams, and now we're going to go from grams to moles. Okay, so the first thing that we do, we're still using magnesium here. We're just going to write out what you're given. Yeah, I swapped these two slides. Just move forward one if you've got it printed. So for which one? That's fine. It's probably, I used a different period. It's just the periodic table issue.
Okay, I just didn't want to get wrong.
Yeah, that's fine. So 8.8 would probably be better than 8.9. It's just, yeah. Yep, if you got 20 or 83.88, that is fine. I think when I actually did this, I used 24.31 was what was on my periodic table. So that's why I did that. Yeah, no, it won't be. No. Okay. Okay, so we write out 73.4 grams. And we now would go ahead, go like so. Okay, so really the only difference in this problem is we're going to basically, for our unit factor, which is our grams to moles, okay, we have grams now in the denominator, and moles is going to be in the numerator. Okay, so we look and we find our 24.305. Okay. So to convert from grams to moles, we know that we're going to have grams in the denominator. So we go to our periodic table and we find 24.305. And whenever we use the periodic table, it's always based upon 1 mole. Yes. Yep. Yep, that's our common relationship between moles and grams. Okay, so grams of magnesium cancel. We're left with moles of magnesium. So I'll check on this one on my calculator first. Okay, so I got 3 point. So we've got 3 significant digits, so 3.02 moles of magnesium. Okay, so same thing here. That's on your. Okay, any questions on those two? You'll get lots of practice. We may have time at the end to do some practice on the worksheets too. So, like I said, it's imperative that you know how to do these. Okay. Next problem. The best way to practice these is just to, or to learn this, is to practice. So, this asks for how many atoms are contained in 1.67 moles of magnesium. Okay, so this time, it's not asking us for grams. It's not asking us to find moles. But it's asking us to find atoms. So, Anderson, what do you think we're going to have to use? Exactly. Okay, so anytime you are asked atoms, molecules, ions, or particles, okay, you want to automatically think I'm going to have to use Avogadro's number in some way. All right? Okay, so if we looked back at that slide, so we're given moles here. So how are moles and Avogadro's number related? What was our setup? 1 mole equals 6.022 times 10 to the 23rd. Okay, so that is our unit factor. That's what we're going to plug into our equation. Okay, but first, the first thing we're going to do is write out what we're given. You can write out what we're given. Go ahead and do like so. Okay, we know if we have moles of magnesium that we're given that we have to have that same unit here to cancel. Okay. All right, so we've got to go from moles to atoms. Okay, we're going to have to do this by using, this is our shorthand for Avogadro's number. Okay, so we know that 1 mole is equal to, what you guys told me, 6.022 times 10 to the 23rd atoms, because that's what we're looking for here. All right, so we have to plug this in. Okay, so what do you think we're going to put in the bottom there at the moles? 1, exactly. Okay, and then in our numerator, we're going to put 6.022 times 10 to the 23rd atoms of magnesium. Okay, our moles cancel. And I'll check this with my calculator. We take 1.67 times Avogadro's number. Okay, we come up with 1.01 times 10 to the 24th atoms of magnesium. Okay. Yes, this is a very common thing. You're bringing that up. Depending on which calculator that you have, you're going to have to learn your calculator. Hopefully some of you have had yours for a while, but I can help you with how to plug this in. Okay, mine is different than some of you. Some of you that have that, the blue, like what he has right there, probably one of the more difficult ones with respect to the algebra that we do. But you're going to take 1.67. Whenever I have an exponential kind of value, or 10 to the whatever power, I always put that in parentheses. Okay, so in my calculator just now, I put 1.67, and I went ahead and put it in parentheses. Okay, times 6.022 times 10. Okay, and then I use the little caret top key to the 23rd. And all of that has to be in parentheses. You'll get wrong power. So if that's happening to you, it's just a calculator issue. And at the end of class, we'll work with your calculator and try to figure it out. But with saying that, be sure you bring your calculators from now on, because we're going to be doing lots of calculations. And you don't want to get on the test and think that you know how to punch it in, and then you're getting the wrong answers. Okay, so be sure you practice using your calculator as well. Okay, did most everybody get this? 1.01 times 10 to the 24th? Okay, so here you just have to remember that 1 mole is equal to Avogadro's number. Okay, so far we looked at just a single monatomic atom. So we were just looking at magnesium, and we converted from grams to moles. We converted from moles to grams, and then we looked at converting to atoms. Okay. Now we're going to look at 3 terms, and I'm going to show you examples of what these mean, so it'll make more sense as we move forward. But the terms formula weight, molecular weight, and molar mass are commonly used interchangeably. So you'll hear all 3 of those terms. Okay, and I have all 3 of those on your key terms, so you can look at those even after we leave. Okay, but they are different. Okay, so if we say the formula weight of a compound, and we're going to look at how we derive formula weights here in just a minute, then the correct term for using formula weight would be if we have an ionic or a covalent compound. Okay, so technically you're safer by using the term formula weight because it includes all compounds. Okay, so that is probably the one you hear the most. Okay, but molecular weight, okay, this refers only to covalent compounds. Okay, so y'all remind me again, what's a covalent compound? Okay, 2 or more nonmetals bonded together, exactly. Okay, ionic compounds, what? A metal and a nonmetal, very good. Okay, so if you use the term molecular weight and you're talking about an ionic compound, then technically that is not the correct use of the term. Okay, the molar mass, you can use this for covalent or ionic compounds, but it's numerically equal to the formula and the molecular weight, but its units are grams per mole. Okay, so we're actually going to use this a whole lot. Okay, so molar mass is what we're going to be looking at mainly. Okay, most students find this pretty straightforward. What we're talking about when we're discussing formula weights, molecular weights, and moles or molar mass is we're going to calculate what the formula weight of a compound is. Okay, so like I said, our previous example, we were just given magnesium, so it was easy. We just went to the periodic table and we looked at the atomic weight, and that was that. Okay, well now we're going to look at the formula weight of a compound. So now we have 2 or more atoms that are involved. Okay, and so we're going to sum these all up. Okay, so if you look at propane, we have 3 carbons and 8 hydrogens. Okay, so we go to the periodic table and we find the atomic weight for carbon, which is 12.01, and we have 3 of them. Okay, so if you have a 3 as your subscript here, then all you do is multiply 3 times the atomic weight of carbon. Okay, and then you take 8 for the 8 hydrogens that we have, times 1.01, because that's the atomic weight of hydrogen, and you get 8.08, and then you add the 2 together. Okay, so that's what you do for a compound. You take the number of atoms, multiply it times the atomic weight for each of the atoms, and you just sum it up. Okay, so let's look at one. This is really as difficult as it will get. Okay, we've got a metal and a polyatomic ion. You guys recognize the nitrate. Remember, that's on your polyatomic ion list. Okay, nitrate is NO3, has a -1 charge. Okay, so that parenthesis right there kind of sets that off to know that you've got a polyatomic ion. Okay, but now we have to look at how many atoms do we have. So like I said, this is really as difficult as it gets. Okay, for our calcium, we only have 1. It's understood that we just have a 1 there as a subscript for calcium. Okay, so we have 40.08 was on the periodic table. Okay, but now we want to look at the polyatomic ion. Okay, the number that is outside of the parenthesis, so the 2 there, okay, it's multiplied by the atoms in the parenthesis. Okay, so we have 1 nitrogen here in parenthesis, but it's multiplied times the 2 on the outside. Okay, so we have 2 nitrogens. Okay, so that subscript says multiplied times the atoms in the parenthesis. Okay, for oxygen we have 3, because that is the formula for nitrate, but we have 2 atoms of nitrate, okay, because we have this 2 on the outside. So we take 3 times 2, and that gives us 6 oxygens. Okay, and so we have 16 for our atomic mass of oxygen. So we multiply 6 times 16, and then we just add all of the atomic masses up. Okay, technically this here says molar mass, okay, and so this would be grams per mole, so that would be our units there. Okay, so I want you guys to, hopefully you have your key terms printed out if you don't, but this would be like something I might ask you on the exam, where I'm going to ask you to find the molar mass of a compound that you're supposed to know. Okay, so this is on page 45 in your book. Okay, but I wouldn't necessarily give you the formula because you would have memorized and learned the formula. Okay, so acetic acid, so you want to find that in your book, and then add up all the atomic weights and multiply them times the atoms and sum up the atomic weight for acetic acid. Okay, so first you got to know the formula. So find that. That's fine. It's written that way because that's how you draw it to kind of, it shows you that the hydrogen's connected to the oxygen. So if you were trying to draw the Lewis structure for it, we didn't get to one this complicated, but that's why it's written that way. But yeah, but you can, if you want to, you can say C2H4O2 if you wanted to. Okay, you've got 2 carbons. So the atomic weight of carbons, 12.01. We've got 4 hydrogens with atomic weight of 1.01. And 2 oxygens with atomic weight of 16. So you should end up getting roughly, depending on your hundredth place, maybe a little bit different depending on the periodic table you use. Okay, but you sum all this up, or add it all up, and we should get about 16.06 grams per mole. Okay, that's the unit that we use for molar mass. Yep. Well, I will give you, everyone will have the same periodic table. So that number, because like I said, periodic tables vary. Some even stop at the 10th place. I mean, it just depends. Okay, now we're going to look at a 2-step problem. I've got it up here, but I'm going to draw through it and talk through it with you guys. Okay. In this problem, we're asked, so now we know how to come up with formula weights for compounds, okay, because earlier we were just looking at single atoms. Okay, and so this problem asks that we find the number of propane, C3H8, molecules in 74.6 grams of propane. Okay, so as always, the first thing we're going to do is write out what we know and go ahead and put our units here. Okay. Keyword here in bold. Okay, if we see the words molecule, atoms, particles, we automatically want to think of Avogadro's number. We're going to have to use that somewhere. Okay, this is going to be a two-step problem. Okay, our common relationship is 1 mole is equal to Avogadro's number, 6.022 times 10 to the 23rd. Okay, so the first thing, we're given grams. So we're going to have to convert from grams to moles first, and then convert from moles to molecules using Avogadro's number. Okay, so we are in grams, so if we add up, I believe we did this on one of the previous slides, but if you add up the formula weight for the molecular weight for C3H8, we should get about 44.11. Okay, so be sure, do you understand where we get this number? So we go to the periodic table, 12.01 times 3 plus 1.01 times 8. Okay, so you just add up the atomic weights for the whole formula. Okay, does everybody agree with that? Everybody, is everyone getting that? Okay, so if we go to the periodic table and we add up the molar mass here, okay, what's going to be in our numerator? Somebody said moles, I think. Okay, so our periodic table, when we add up the formula weight, it's always based on 1 mole. Exactly. So we're going to have 1 mole here in the numerator. Okay, so earlier, if we were just asked to find moles, we would stop here because we have moles left uncanceled in the numerator. Okay, but we're asked to go to molecules. Okay, so we know if we have to go on another step, we'll go ahead and write out our fraction here. Okay, so now we have to use this relationship, our 1 mole equal to Avogadro's number. Okay, we know that our 1 is going to go down here with our moles, and 1 mole is equal to 6.022 times 10 to the 23rd C3H8 molecules. Okay, we're asked to find molecules of propane. Okay, so our units should match what we're trying to find. So we have found propane molecules. Okay, and once again, you want to be sure you know how to use your calculators here. So however you want to do this, but you multiply everything on the top, multiply everything on the bottom, and then divide the denominator into the numerator, just like you did for dimensional analysis. Okay, so I'm going to check this real quick. It should be 1.02 times 10 to the 24th, but make sure. Okay, some of you can plug it all in at one time. You have one of these scientific calculators. Okay, so yeah, we get 1.02 times 10 to the 24th molecules of propane. Okay, so far, if you have had to plug in moles, okay, this will change for chapter 3, but right now, if you've had to plug in moles, it's been 1 mole, right? Because we have 1 mole is what our periodic table is based upon, and then our common relationship between moles and molecules is based upon 1 mole. So here and here, all these places that we've plugged in moles has been 1 every time. Okay, so just a little bit more practice here. Yes? 1.02 times 10 to the 24th molecules. Yes. Yes. Okay, you're going to divide by 44.11. Yep. Okay, any other questions? Okay, so just going to do another practice problem here. Okay, we're asked for how many moles and then molecules. So you can put this all together as one big problem if you wanted to, but we're just going to do it kind of stepwise. Okay, so this time we're given grams of ozone. And the first thing we're asked is to go to moles. So that's what we're going to do. Okay. Okay, so you guys tell me what's the formula weight for ozone. Okay, where'd you get 48? Okay, so our atomic weight on the periodic table tells us that oxygen has 16.00 is the atomic weight. Okay, but we have 3 oxygens, so we're just multiplying times 3. Okay, so we end up with about 48 as our formula weight. Okay, so we went to our periodic table. Some of you may have known that off the top of your head, but it came from the periodic table. And so it's always based upon 1 mole. We have 48 grams per 1 mole of ozone. Okay, so if we were to stop here, we would get our answer. So we would get our moles. So we cancel here, and we take 60 divided by 48. We would get 1.25 moles of ozone. Okay, so if we were to stop right here, okay, so that would give us the answer to A. Okay, but B asks to go to molecules, so we don't have to rewrite all this. We can just add that last step on there. Okay, so we've got moles of ozone. So we know we've got to have moles in the denominator. And we're asked to find molecules. So we know we're going to have to use Avogadro's number. And 1 mole is equal to 6.022 times 10 to the 23rd molecules of ozone. Okay, so punch this in your calculator. Be sure you use the parentheses when you need them. Okay, so we're going to find our answer should be molecules of ozone. Okay, what did you guys get? What's your answer? Very good. So you got about 7.53 times 10 to the 23rd. So a very large number, which obviously you would think so. Okay, so if you have 60 grams, that's what we would measure out in the lab, which is for not really on industry level, but for here, that's a pretty large amount. Okay, so in that 60 grams, you have 7.53 times 10 to the 23rd molecules of ozone. So that is obviously a large number contained in that 60 grams. Okay, so you can break it up into 2 parts. That's what was done here. So you found your 1.25 moles and then go from there. So either way that you want to do that. All right, I want you guys to do this one. Find the mass in grams of this amount of SO2 molecules. Okay, so this time you're starting with molecules. Okay, so your first step is going to include Avogadro's number. Okay. Yep, it's just kind of backwards from the ones we just did. So this time you're starting with molecules instead of with grams. So you're going backwards. Okay, so our first step, the only common unit that we have is that we are given molecules. So the only common relationship we have here is that 1 mole is equal to Avogadro's number, or that many molecules. Okay, so really this is just kind of the reverse of what we did earlier. We went from grams to molecules, and now we're just going backwards. So really we're going from molecules now to grams. Okay, we don't have a direct relationship between grams and molecules. Okay, so we have to go to moles first and then convert to grams. Okay. So in 6.022 times 10 to the 23rd molecules, there is 1 mole. So the molecules, Avogadro's number now is going to be canceled out, and we have molecules in the denominator. Whoops, I didn't mean to put molecules there. Whoops. Okay, so we're left with moles. Okay, but we're asked to find grams. Okay, so we just have to add that one step. We now, from those problems earlier, all we have to do is convert from moles to grams. That's all we're doing here. So in 1 mole, okay, we've got to find the grams for SO2. We know this is in 1 mole because we're looking at the periodic table. It looks like I found it to be about 64.07 roughly in there. Okay. So we have 64.07 grams. And this is based on 1 mole. Okay, so now we're left with grams in the numerator not canceled out. So we should get about 1.06 times 10 to the negative 15. Is that what you guys got? That's right, 10. Okay, so once again, this kind of shows you that in a very small amount, if we were to measure this out, so times 10 to the negative 15, so that's a very small mass, we still have 10 to the 6 molecules contained in that very small mass. That's why we have to look at these as moles instead of grams. There are none that we have here. Very expensive. They, can measure for something that small. No, not here, but labs do have that kind of equipment. Yep. You can actually put samples like that in really large, they wouldn't be necessarily a balance per se. It'd be like a very large instrument, and you insert it in there, and from the force, it's a lot more complicated than if you have to be really exact. So. Okay, this won't take but a minute. This will be the last thing we go over. We're going to look at percent composition. This is also called percent by mass. So you're going to actually do a lab. It's not this week. It's the next lab, I believe, that we're going to do percent by mass. But percent composition is you're taking the mass of each individual element in a compound, and then you're dividing it by the total mass of the compound times 100. So basically it's like part over whole times 100. So you want to find out what percentage of this compound is carbon, or what percentage of this compound is hydrogen. Okay, and so all you do, if you're looking for the percent composition of carbon, okay, you're going to take the mass of carbon, okay, and here we have 3 carbons, right? So we have to take into account all 3. So we have 3 times 12.01, which is our atomic weight for carbon, and then we divide it by the total mass of the compound. Okay, so if we added up the total mass, we did this earlier, so we came up with 44.11, okay, and then we multiply times 100. Okay, so you take the number of atoms times the formula weight, or the atomic weight, times the atomic weight of carbon, or whatever atom you're looking at, and then you divide it by the total formula weight of the compound. And you get, here, it'd be 81.68%. Okay, so if we were to think about our hydrogen, okay, so we can go through and calculate it, okay, but if you add up the percentages for all the components in your compound, it should equal 100%, okay, so we're doing a percentage here. So we're going to look at, you could do the calculation with hydrogen. Yeah, exactly. So you wouldn't necessarily have to go through this. If you only have 2 atoms and you found one to be 81.68%, you know the total percentage has to be 100. So 100 minus 81.68 means that hydrogen has to be 18.32% of the compound of propane. Okay, but just to show you how you could go through and you would get the same thing, you would take the mass of your hydrogens, so you have 8 of them, times 1.01, and then divide it again by the total formula weight of the compound. Okay, and times 100, and you get 18.32. Okay, so we're going to end with this one. I want you guys to calculate the percent composition. Okay, so you have a polyatomic ion. This involves you having to know how many atoms are there. Remember to multiply times the number outside the parenthesis in the parenthesis. And I want you to calculate the percent composition for each atom. Okay, so for iron, for sulfur, and for oxygen. Okay, and when you add those percentages up, you should get 100%. Okay, the first thing you might want to do is just add up the formula weight first for the whole compound, because you know you're going to have to use that. put it up here and see if you guys are getting the same thing. Did you get your calculator to work? Oh, that on? Fractions. There you go. You push that up there, and it takes it out.
So I do that every time?
No, I think it's on there. Oh, I get what you're saying. Okay.
And sometimes it doesn't come out the same, so, but I've got it.
Yeah, when you get your answer, I mean, it's the mode it's on, but you know to just push that,
Okay.
and it'll. Did you know to do that?
Well, I was going to push shift and enter.
Oh no, just all you gotta do when you get there, just push that. But I can look at it longer. It's probably just the mode it's in. I can probably get it out. But yeah, all you gotta do is one extra click to see it and get that. Okay, we have 2 iron atoms. So we multiply the 2 times, here I've just got to the 10th place, so you might be using a periodic table with more significant digits. But 2 times 55.8, okay, the total formula weight for the iron 3 sulfate is 399.9. Okay, so we divide the mass of the iron by 399.9 times 100, should get about 27.9%. Okay, we have 3 sulfur atoms, so it's understood we have 1 in parenthesis, but you have to multiply it times that 3 on the outside. So we have 3 times 32.1 divided by the total formula weight for the compound times 100. We get 24.1. For oxygen, we have 4 times 3 oxygens. So we have 12 oxygens. So we have 12 times 16 divided by the total formula weight times 100. So we get 48.0%. So we have the highest percentage here of oxygen in the formula. Okay, and so when we total these up, we should get 100%. That's a way to check your answer to be sure that you've done the percent composition correctly. We will pick up with what's called molecular and empirical formulas on Wednesday. So if you want to be reading about those, reading ahead would be great. Also for lab, we're doing 2 labs today. One is posted on Blackboard. I apologize, it's not in the lab manual, so be sure you have it and your lab manual for chemical bonding. But other than that, you guys have a good day.